All right, so I'm gonna have to repeat myself. Yeah, today we're gonna be talking about generating functional for massive scalar field, and the starting point is the generating functional z of j is it's a path integral over all field phi with the action, and here's the source included. J is called source, right? J is a function. If I want to describe it, I'm not sure if it's already clear. It's like the semi-classical, this is called semi-classical approximation in physics. When you have a quantum system in some background. When you solve an atom, the equations of, you quantize an atom in some background electric field, you're doing semi-classical physics. You're treating electric field, photons, that's classical, but the particle is quantum. Semi-classical physics is all over the place. Here, J is some background produced somehow, right? And we're just treating it as classically. It's just a background. Good. All right. By the way, it's the same for fine temperature physics, right? Thermal background is a background provided by other particles by the environment. So the free action is, let's just use the notation of S naught of phi for free action. Here's how you can write it. This is just, you recognize this is a quotient of motion and anticipation for the Feynman propagator. I've already shifted by I epsilon. Shifting it like I epsilon this way picks up the time ordered Feynman propagator, hopefully, if you recall, because there are two poles and you're going diagonally like that. All right. So Z naught of J we solved. This is Z0 of 0, free theory. This is just overall normalization. All the divergences are pushed in there. Exponential minus half integral of J xy jx Feynman propagator jy. We wrote this, right? This is this symbolically what we drew here, right? All right. What is the endpoint correlation function? The endpoint correlation function is, here's the interacting vacuum. It's a time-ordered insertion of these operators. And the way you find it is by dividing by 1 over zj, taking n derivatives of zj with respect to jx1 all the way, setting j equals 0 at the end. The time ordering comes naturally, right? I epsilon thing. Now, I also commented, this is for you guys to figure out, but I'll do one explicit example of 4-point function. But if you take the log of generating functional, that has a name with a minus sign. It's called effective action. If you take derivatives of effective action directly, what you're going to get is that you're going to compute the connected correlators, right? So that's what you're going to do, connected correlators. Is it clear what connected correlator is? What is a connected 4-point function? What's the value of the connected 4-point function in free theory? Okay, so then you don't know what connected correlator is. What's a connected correlator? What's a connected 2-point function in free theory? Yeah, it's Feynman propagator because the 1-point functions vanished. What is the connected 4-point function? What's the connected 3-point function? Zero. What's the connected by Z2 symmetry? What's the connected? But the connected 3-point function is just the 3-point function because of there are no 1 points. What about the 4-point function? What's the connected 4-point function in free theory? Is it clear what connected means? maybe that's what the issue is. What did the 4-point function look like in free theory? What were the Feynman diagrams? Exactly. Here it is. Right? So we this is G4, and then before you transform this, right? here are 4 points. There was this, there was this, there was this. Are these graphs connected? No, they're not connected. Connected means that if you chop the, if you cannot split it, it's not connected as a manifold. It's not connected. It's not connected. Right? So what is the connected piece of the correlator? 4-point function is this minus these 3 terms. Right? What would it look like? It would look like this. We're going to derive that. Those are interaction terms. Right? All right. Taking this log, is it clear that the can you see from that expression, evidently, you don't need to know anything. You could have just plugged in that relation and told me that the connected piece of the correlator is 0 for free theory. Why? What is z of j for the free theory? Right? This is an overall normalization. It's exponential of this. Take the log of it. What do you get? You get an integral of xy jx, jy, this thing. How many? So if I take one derivative with respect to j, I have one j left. So setting j equals 0 kills it. If I take 2 derivatives, I get Feynman propagator. What do I get if I take more derivatives? I have jx, jy. What do I get if I take 3 derivatives of j? 0. So all the connected correlators are above 2 point are 0 in free theory. What would an effective action look like if it had to have some connected piece? It would be higher order than j, right? Is it clear? Any questions? Here are the free correlators. Yeah, I think I went over this. I absolutely recommend that you definitely play around with this idea of connected correlator, Wick contractions. All of these should become very intuitive. That's how physicists talk about interactions. All right, so now we're gonna do interactions. So now we're gonna get connected correlators. What's the starting point? The starting point is z of j is as before, path integral over phi, e to the power of I s action. But now next to the free term, you have an interaction term, v interaction phi, and then j phi. This v interaction is also down here in the normalization. Oh, I'm sorry. Good. All right. So we said that this expression is the we didn't say this, it's obvious that this is the expectation value of the time ordered exponential of the source term, exponential of this term in the interacting vacuum, right? What is this? This is the norm of the interacting vacuum. Is that clear? Or we literally went over this, right? When we related path integrals to expectation values, correlators, this is what we did. Yeah.
That interacting vacuum, how can we understand it? Because it isn't annihilated by any annihilation.
Sorry, what? Say it again. Say it again.
So the free vacuum is annihilated by A, by always. This one, the interacting vacuum, is also annihilated by.
Need not be.
How do you formally define it?
I define it for well. For how do I formally define it? It's quantum mechanics. What's the vacuum? You have a Hamiltonian. It's the lowest energy state. Your Hamiltonian is positive, so it's a 0 energy state after you get rid of the infinities. Right, that's our definition from quantum mechanics. I told you how to calculate things in it using path integrals. Right? I even told you how to, yeah.
So we don't care what this state looks like. You just know it's just the ground.
What do you mean by what this state looks like? I'm giving you all the correlators of it. What do you need more than that?
This is Feynman law, right?
It's what?
This is Feynman law.
I don't know what that is. No, sorry. Do you guys recall we went through this? I said that path integral is a reformulation of quantum mechanics, and we literally had this expression that if you want to know what the expectation value of something in an interacting theory is, this is the way to calculate. Of course, something that I'm hiding is that I did this extra trick of t going to t multiplied by y1 minus I epsilon and epsilon going to 0. Right? That was also to tame the divergences. All right. Okay, so this is what the this is what it is. Sorry, I think I'm just dropping all of these zeros. It's normalization. So take this guy and expand it. What are you going to get? You're going to get the sum. This is an exponential of I to the power of m over n factorial, integral of dx dm, jx1 to jxm, the time-ordered m-point function in the interacting vacuum, otherwise known as gm of x1 to xm. Right? This is the Feynman correlator, time-ordered. All right, let's write this down diagrammatically. What's the first term? 1. Right? What's the second term? There's a J, and then there's G1. What is G1? Vacuum one-point function of the interacting theory. Then there is 2 J's, 2-point function, G2. These are the interacting theory 2-point functions, so on and so forth. Right? This is the diagrammatics of it. But importantly, here you have connected things as well. Previously, a z of j was this thing, exponential of that. If you expanded that, you're going to have a line squared, which is 2 lines, line cubed, which is 3 lines, and so on and so forth. You're never going to get connected stuff, right? But here in the expansion, there will be connected stuff. Will I get a 1-point function? Is it possible to get a 1-point function? When do I get when am I guaranteed I'm not going to get a 1-point function? Yes, but what was the origin of it? Z2 symmetry. Here, what has changed? I have a V interaction. If my potential still has the Z2 symmetry, same argument will go through. What kind of potentials have Z2 symmetry? Give me an example. Well, 5 squared is free here. Phi 4, lambda phi 4. So lambda phi 4, the vacuum will remain, the 1-point function will remain 0. Phi 6, phi 16. Your favorite thing that's Z2 symmetric, right? But if you take phi q, phi 5 or something like that, it won't be. Should you be concerned with that or not? Mm-hmm. For correlators, yes. No. We'll see. You'll see. Okay, so this is a sort of symmetry breaking. Think about that. Okay, we have not discussed that, but I want you guys to think about that. What that looks like, what does it mean to have one function? There's a reason that in quantum field theory, people start with talking about lambda phi 4 term. We had the lambda phi squared term, sorry, the m squared phi squared term. Why not pick phi cube? What's wrong with phi cube? No, that's not the issue. The theory is sensible, actually. It's still relativistic. It has Poincare invariance. Think classically. What is wrong with adding a lambda phi cube term? What principle will be violated? Yeah, exactly. You're not guaranteed a minimum, right? So the theory might be unstable. The one-point function, developing one-point function is related to that. Anyway, so I'm going on a tangent. Let me just continue. All right, so this is what it is. This is the general expansion of it. And of course, when you take derivatives that set j equals 0, you read off these terms, right? These are the total correlators, right? If I were expanding log of zj, then these will be the connected pieces. These are blobs, right? These blobs are like the inside of them there could be disconnected pieces. All right. So what is the main tool in our arsenal? Schrödinger-Dyson. Schrödinger-Dyson says the following. I think I've used this slide several times before. So I said if you have a path integral with some measure and some f of phi, del s of phi, this is the same thing as putting an I here, path integral, del of f, derivative of phi, f with respect to phi. It's just the fact that you could repackage these two terms as path integral of del phi of something, right? And that's just by the virtue of the fact that path phi is a dummy variable, it shouldn't matter. So this you get this equation. Now pick your phi to be the source term. We did this before. What you obtain is what's called the Schrödinger-Dyson, or a particular case of Schrödinger-Dyson. And then you learn that you have a differential equation of this form that your partition function, generating functional, I might just say partition function from time to time by mistake, but you know what I mean, satisfies. Good. This never uses free theory. This is just true for any interacting theory, fully non-perturbatively. Are there any questions? Because we're going to be using this a lot. All right. So Schrödinger-Dyson simplifies calculations a lot. Let's see how. Take the action, a massive scalar field plus some sort of interaction. I'm not going to even specify what interaction. V interaction of phi. The only thing is that it's only a function of phi and not time derivatives of it. What would go wrong if it was a function of time derivatives of it? What are the time derivatives of phi in canonical quantization? Pi. You had to do your path integral in the phase space. We use the fact that the Hamiltonian was only pi squared, right? That's why I don't put any del T phi, and that's why people don't put del T phi the terms over there. But there are other reasons. What other reason can you imagine? What changes? Why don't you add this term to your action? Oh, what's the simplest answer? Somebody can answer this. What can I write as my potential? Well, I can't put del T phi. Is that obvious why? What principle violates? Lorentz invariance. So I can put del mu of phi, but I have to contract indices, right? So I can put del mu phi or something like this. I can put del mu phi to the power of 17 phi. These are all Lorentz invariant, right? I can do Well, actually, yeah, I can do del mu of phi, del mu of phi to the power of 15 phi squared, things like this. Can you tell what is going wrong if we're doing this? Think about this. I'm not gonna go on different tangents, but think about it. Then, like quantum field theory is one of there are lots of choices that you're presented by, and by now you have everything you need to know why these choices are not choice, why people don't make these choices and pick other choices, right? All right. So here's the action. And what we're gonna do is we're gonna do Schrodinger Dyson. So del S del phi. Del S del phi will give me this, right? And then at the end I have to set phi as del del Ji. So here it is. This is the very first term, right? Then the second term, the first term applied to the interaction will give you del of v del phi. That's v prime, and for phi you're gonna put del J, right? And then finally, I don't know why I have minus and plus. Correct sign here. Minus or plus. I don't remember my convention. I've probably changed it a million times. So this is what the differential equation is, that in the interacting theory, the generating function will satisfy. Good. All right. What do I get if I set J equals 0? If you set J equals 0, you get this equation. Well, you first take the derivative and set J equals 0, right? So you get the fact that the Klein-Gordon operator acts on the 1-point function. Is it clear why 1-point function? Right? I'm multiplying by dividing by 1 over z naught. And then the time ordered v prime. V prime is force, basically. So what does this equation tell you, right? This equation tells you that in the interacting theory, the 1-point function is related to the extrema of the potential. Let's stare at this and see if you guys see this. In QFT2, we make a big deal out of this, and we'll explore this in detail quite a bit. But that's what the 1-point function is. Right? You get more equations by taking more derivatives with respect to del I del J and setting J equals 0. So the next equation that you obtain is minus, again, the Klein-Gordon operator acting this time on the 2-point function, because I'm taking 2 derivatives, right? Plus the expectation value of phi v prime is equal to minus I this delta function. Can you see where this delta function comes from and why there was no delta function here? Okay, I leave it to you guys for you guys to figure out, but the hint is that the correlators are time ordered. the time ordering involves a bunch of heavy side functions. This comes from that. But you should do the algebra and see term by term, convince yourself this is the next short term. So, okay, this was the interpretation of the 1-point function. What's the interpretation? These are, by the way, these are fully non-perturbative, fully quantum equations. I cannot stress this enough. Like, this is why it's important to stare at them, because this is all that there is to QFT. The equations we're going to go through, we're going to take a bunch of derivatives. And if you could solve these equations, you have solved a general interacting quantum field theory. That's all that there is to quantum field theory, right? So that's why it's important to interpret them term by term. What is this? If the potential was 0, this term would go away. What would you find? You'll find that the 2-point function, you'll find that the propagator is the Green's function for the for Klein-Gordon operator. Here, what you find is that that equation is still satisfied, but with this extra modification term that is related to the interaction. Now, what does this modification term look like? If my interaction term is 5,4, what order is this? If my interaction term, if V is 5,4, what is V prime? It's 5 cubed. There's I have another 5 here, so this is a 4-point function, right? If what it tells you is that the propagator, you used to have an equation in terms of the 2-point function that you could solve. Now that 2-point function equation is coupled to the 4-point function answer. So you can't solve it. You have to write down the equation for the next one, and the next one, and the next one. If this is 5,4, this means that to solve for the 1-point function, you need to have the 3-point function. What you end up by taking infinite number of derivatives order by order is that you get an infinite set of equations that relate low-point function to higher-point functions. That's what these equations are all that there is to quantum field theory. If you could solve them, you have solved non-perturbative quantum field theory, but we cannot solve them, right? This is the magic of path integrals. Using path integrals, you could write down a set of equations that all the correlation functions of quantum field theory will satisfy. And if you could solve them, you would be done. All right, example, let's just look at this a little bit more carefully. As I said, this is lambda 5,4. The 1-point function is related to a 3-point function, but at the same points, coincident points. The 2-point function is related to the 4-point function where 3 of them are at the same point. Why are these at the same point? Can you tell? This is V prime. What is V? What is V? Lambda 5,4, V is integral of dd d4 dd of x 5 x to the power of 4. Right? So if you take derivatives, you only have 5 x's. This has to be there because there could be a contact term here. So this is your next equation. Remember this equation because like it will really help you understand perturbation theory. The way we go through in this, the way I teach it, the way we go through perturbation theory is really in your face, but you have to really understand these equations and like work with them. All right, what these equations do is that they relate lower point functions to higher point functions, right? That's a little bit, that's not very desirable because you want to solve for 2-point functions. Oh, you need to have you should have had the 3-point function. So we want to find the 3-point function, you should have had the 4-point function. That's not very helpful. It would be nicer if you could write it in such a way that the higher point functions are related to lower point functions. So you start with like G17, and then you say, oh, I need G15, 16, 15, and you go all the way down. Now you have a finite number of equations, you could try solving. You could do that, and we do that here. You write these as integral equations. How do you do that? Let's see how to explain this. Well, you just basically, the idea is that you multiply let's start with here. You multiply this with a Feynman propagator and integrate. That's a homework problem for you guys to see that for lambda phi 4, this you could keep repeating this. You get an infinite set of integrals. You could turn them into a set of integral equations of this form. These are formal non-perturbative equations. We cannot solve them. One comment for those of you guys who, well, we didn't go through Feynman axioms or anything like that. There's something profound that's happening. In quantum field theory, there was a question earlier, where is the state? We are used to think of the Hilbert space, operators acting on it. We talked about that in the language of canonical quantization. We only did that to your free theory, right? Here, what we're saying is that every path integral, if I first convince you guys, the path integral formulation, hopefully I did convince you guys, is a reformulation of quantum mechanics. The objects of interest are these correlators. And these are functions. Quantum field theory could be thought of, forget about Hilbert space, all of that is a sequence of functions that satisfy these equations. The story of Feynman axioms are about another approach to quantum field theory, which is based on this idea that you start with these functions, a set of correlators, a hierarchy of functions. There is G1, G2, G3, G4, all the way. There's a hierarchy of functions. You start with them. They have to satisfy a bunch of criteria, equations. If they satisfy them, you prove there's a Hilbert space. There are operators and everything. You reconstruct the Hilbert space from this. That's the other approach to quantum field theory we've not talked about, right? And that object, in that way of viewing things, you start with these guys as constructively. These are the objects that you work with, right? You start with a bunch of correlators, and you construct the Hilbert space and everything from that. Good. So what is neat about showing your Dyson is that it makes that very explicit. All right, so what we're going to do, we're going to try to solve these equations in perturbation theory. What do I mean by perturbation theory? Previously, when we were talking about perturbation theory, if you recall, there was these, I had to do expansions, right? So I had e to the power of I s naught, and then there was lambda s interaction. I had to assume this term is small, bring it down. We had to play these games, right? Here, you could, this is equivalent, but you could totally be sort of, you could ignore that picture completely and say, well, what is quantum field theory? It's a set of functions, or these are not functions, by the way, these are distributions. Let me correct myself. These are distributions, right? They are multivariables and they're distributions. These guys admit a series expansion, Taylor expansions in lambda. That's it. That's what perturbation theory means. Right? These functions are analytic functions of lambda. Done. Expand. Taylor expand. We're going to derive perturbation theory this way. Most textbooks do it a little bit differently, but I found this a little bit more elegant. Good. Now that we expand it this way, because we know those GMs of 0, when lambda is 0, we could solve. There's a hope of solving those equations, order by order. Recursively, we solve them. All right, so here is this perturbation theory. we're after this thing. We're gonna try to solve this equation, Schrödinger Dyson, and this is our action. I said that before. Oh, actually, aha. Let me just make even a more no, it's not a claim, it's a fact. Something a nice observation. As a matter of fact, you could formally write down the answer to that differential equation. You could formally write down the solution to the path center, that equation, the generating function of on field theory. As you can see, it's this. This is the generating function. It's a formal solution. You could check that it solves this. It's a little bit formal, so it's actually not at all useful. So, all right, let's see. How do you want to? Yeah, let's jump to lambda phi 4. Good. So what we're gonna do? Oh, actually, I think I'm gonna do the lower the partition function. Okay. Here's our zj, and I'm gonna divide it by z0 in the interacting theory. So I had this e to the power of I lambda phi 4 here, right? This expression, where is it? I did not write it. Yeah, no, I wrote it here, lambda phi 4. So take S interaction to be S lambda phi 4, and we're gonna expand that lambda phi 4, exponential of that as 1 minus I lambda blah. We saw before that this is going to be the correlator. That's why these expansions in lambda, if I have a lambda downstairs, I have lambda upstairs. If I further expand in lambda, the answer would be expansion of G's, right? Correlators, time order correlators. Okay, so here's the exponential on the top, here's the exponential on the bottom. It's convenient to factor out this one piece. So you're dealing with 1 minus I lambda over 5 factorial, this expression. You know all of these expressions, right? Let me, what is down here? What is this expression? You've seen this before. This is the free time order 4-point function. Isn't it? Integrated. So we're using a knowledge of free theory. Here's the same thing with the J's in it. All right. Let's further expand the denominator. So we have just an expansion in lambda. It looks like this. Zj over z naught. These are free theory expressions we can pull out for simplicity. It looks like this. It's 1 minus I lambda over 4 factorial. This integral minus this integral. Let me explain. So this piece is the numerator. This piece is the denominator. There's an extra minus sign because I'm inverting this lambda, bringing lambda to the numerator. Good. So there are these two terms. Are there questions here? Let's first massage the first term. What is the first term? As I said, this is just a 4-point function in the presence of sources. So this is z naught of j with 4 j derivatives, 1 over z naught of j, right? This is this term. What is this term? This is you take 4 derivatives of j, but you don't divide by this z naught. Instead, j equals 0 at the end. We know z naught of j explicitly, so we could expand this expression explicitly. Let's focus on the first term. This is something that you'll do in the homework, but let's focus on the first term. There are three terms coming in. The first term is going to be the propagator from x to x squared. The second term is going to be the propagator from x to x, propagator from x to z, j, z. And the third term is going to have, sorry, this has two j's. So this is a term with no j's. This has two j's and this has four j's. Is it clear, or are you guys lost? You seem very lost. These are functional derivatives. It's not. So what I'm doing is this. I'm doing 1/z naught j del 4 del I del jx1 I del, oh no, jx4, sorry. I to the power of 4. What am I taking derivative of? Exponential of minus half integral of jx I prime delta f minus y prime j y prime. So there's some derivatives and functional derivatives that you have to do. There are these three terms. Don't be sloppy with the Dirac delta functions. That's how you get all these terms. All right. Diagrammatically, what does this mean? The first term says is two propagators from x to itself. The second term is 6. There are two j's and then a propagator like this. And then the last term has 4 j's. Good. I'm putting these guys separate because when this is integral squared, so there is jz and jz prime in it. Right? All right. The first term has no j dependence. This term also has no j dependence. It turns out that these guys cancel to all orders. That's actually surprise. It's not. It was obvious from by construction that is guaranteed. So this term goes away. That is actually what the job of the second order term is. So you're left with these two terms. The factor 6 comes from just combinatorics. Can you see what the combinatorics is? So you have a 4 lines and 2 crosses. There's 4 choose 2 ways of connecting them. That's 6. That's the combinatorics of the diagram. And then the last term has 4 j's and these guys meet at the point. At that point is x. These are Feynman diagrams that describe your calculation of this order. What are we calculating at this order? What was I calculating? The generating functional, right? All right, so what does it look like? At the first order, you get this expression. This is the generating functional of the interacting theory, normalized. Is the generating functional of the non-interacting theory normalized, multiplied by 1 minus the first order correction, and so on and so forth. Right? It should be obvious that all of these guys should have crosses, right? All right, so let's focus on these terms. I think here I'm again doing the same stupid thing. So this is 1 minus I over lambda 4 integral over dx of, what is this? This is the propagator 0, right? Del f of xy jz squared. What is this? This is just del f of x z jz to the power 4. What did we do? We calculated diagrammatically in terms of integrals the generating functional of the lambda phi 4 theory to the first order in lambda. Good. Why did we do this calculation? So that we could take derivatives and calculate correlators, right? We're going to do that next. So what do you expect? So the correlators, what are the correlators? There is G1 as a function of lambda was G1 of 0, which was 0 plus lambda, and this is the correction I want to calculate. What is it? We said it will be 0 because we still have the Z2 symmetry. Lambda phi 4 has Z2 symmetry, right? This is the 1-point function. This is vacuum of the interacting theory, right? Fine. Good. Now, what's the 2-point function? So the 2-point function was I delta of f of x minus y. Now there will be a 1 plus lambda something that we're going to calculate. Good. 3-point function was 0, remains 0. 4-point function was 0. Sorry, the connected 4-point function was 0. Now it picks up a lambda term. We'll see that. All right, let's start with the G2. This is my generating functional. You take derivatives with respect to j twice and set j equals 0. The result is this. You get minus I, sorry, you get the good old free propagator minus I lambda over 2 I delta f0 this integral. Diagrammatically, what does this look like? It looks like this was your old propagator. Now you have a point x in the middle and you're doing a loop over this. These are Feynman diagrams in real space. Good. Let's pause here. Is it clear what the deal is? This delta of f of 0 is this loop, and this delta of xy is this, delta of xz is this. There are i's associated with it. Then there's minus I lambda that sits outside. This factor of 2 is the symmetry of the diagram. If you flip these two guys, it's a symmetry factor. So this is the first order correction to the propagator. From Schrodinger Dyson equations, remember the propagator was the good old propagator plus a term that was coming from the interaction, and this is what the interaction term is. The contribution of the interaction term is. This solves the part of the Schrodinger Dyson equation that was just a Green's function for the Klein-Gordon equation, and this cancels the extra contribution. All right. Should you guys be concerned at this point? Is there something weird or sketchy? We're calculating the propagator of the interacting theory at the first order in lambda, and this is what the expression looks like. Is there something that is concerning here?
Isn't the propagator singular with both points on the street?
Exactly. You have delta phi of 0, delta of f of 0. That blows up awfully, right? So that's a divergence. What the hell are we talking about as a perturbation theory? So we'll see that. There's a good reason for that. Do you know what the reason is? I've already said this. What are you trying to do? You're trying to solve quantum field theory. What did I tell you? You absolutely need to define quantum field theory. Cutoff. You didn't assume any cutoff. That's what their problem is. Right? That's why there are divergences. Quantum field theory is ill-defined without cutoffs. Good. So we will cut this off, regulate. We'll regulate this diagram later. That will be in 2 lectures. But for now, let's just be oblivious of that and just continue. What are Feynman diagrams? Well, they're Feynman rules. Every time you have a propagator, you draw this line. Feynman diagrams, these expressions, as you can tell, get really ugly in terms of integrals. So these Feynman diagrams are short form notation to first build intuition about these integrals and also write them down, right? Previously, we saw a version of this in 0+1 scattering theory. All right, so this is a propagator. Every time you have a vertex, you put minus I lambda d+1. This is space-time of x. And every time you have a cross, you put j of x at that point. Actually, if there's no line attached to it, you don't want this bit either. There's no line attached to it. And then you have to divide by the symmetry factor. What do these mean? It means that now these are the rules that will tell you what the hell is this diagram. This is a diagram we draw. What is this? This is an integral. This is an awful integral. We first put points here: x1, x2, x3, x4, x5, x6, x7, x8, x9, x10, blah, blah, blah. This is a propagator. You will identify external points. Well, there will be a bunch of crosses actually as well. There will be a bunch of crosses. Every such process comes with a factor of j, right? At that point. All these middle points you integrate over. There's an integral coming from each of these middle points. These are propagators, and that's it. Every vertex comes with a factor of minus I lambda. You stare at this, and if there is some sort of a symmetry of the diagram, you divide by the symmetry as well. That's what this diagram represents as an integral. So instead of filling the whole board by millions of integrals, you just draw a bunch of diagrams. It really, really simplifies your life. All right, so these are Feynman diagrams for lambda phi 4. In real space, these are real space ones. As you can guess, it's a little bit these are a little bit annoying, right? Because delta of f, the propagator, in real space was kind of weird looking. It was a Fourier transform of 1 over k mu minus m squared plus I epsilon. This Fourier transform, right? D of k e to the power. So it means that, well, because the Fourier transform is easier to write, maybe you should be doing Feynman diagrams in Fourier space. There's nothing wrong with doing it in this. It's just you can't be super explicit about what delta f is. Whereas if you did it in momentum space, you can literally write down to every of these lines, this corresponds to 1 over k squared, blah, blah, blah. Right? Yeah.
Why don't we get free particles? I mean, all of these particles have finite propagation, right?
Yeah.
Then where are they?
What do you mean finite propagation? These are, I'm calculating a correlation function with a bunch of points in it. So if this is a calculation, so if this is a Feynman diagram that contributes in some limit to some correlator, there will be in that correlator, say it's an endpoint function x1 to xn. Those are data of my theory. So there will be those, the final answer will have those. What other positions that come in to play in these diagrams will be integrated over. Right? That's extra things. Good. All right. Similarly, in the momentum space, you'll get the correlators. So every external leg, well, actually, maybe it's clear what external leg means, right? All right, good. All right, let's just get back to our calculation of the 2-point function. Then we're running really behind. Correlation functions have no sources, so they have no external legs. I'm not explaining what external legs are. So we're doing correlation function. Let's not jump around. So the 2-point function, the free part of it is just the propagator, right? And then here's the interaction term. There's a factor of half and blah, 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 the suppressing here. And then there's lambda squared. Well, actually, no, there's no factor of half. That half comes from the symmetry of this. All right, so what is this diagram? By the rules that I was just discussing, there is a vertex here, it's minus I over lambda. There is a symmetry of 2, that's 1 over 2. There is this propagator, I delta f of 0, right? Then there's this propagator and this propagator. Good? And those two propagators take this form. Why? Because this is x, this is y. Let me put the labels. This is x, this is y, this is z. One of them will have a Fourier transform of this with e to the power of y minus x, I y minus x, blah, blah, blah. The other one will have the Fourier transform of this with e to the power of minus I k x minus z. So the x disappears and you're left with this guy alone. All right, very. So what is this guy? This is the propagator in momentum space of the free theory. So if you Fourier transform everything, you learn that the propagator in the interacting theory is the propagator of the free theory times 1 plus lambda over 2 delta f of 0, this piece. Right? That is just the fact that I'm writing this plus this cartoonishly as this times this. Right? That's what I'm doing. This is a cartoon. We don't want to do this. Good? The reason I do this is the following. To the first order in lambda, I can think of this as same expression comes from the Taylor expansion of this. To the first order in lambda, I can view this as a shift in mass. The only parameter in the free propagator is mass. So I can capture this as a shift in mass. Now, what is this? What was the propagator? The propagator, we found the propagator by doing intervals, various propagator, found propagator by doing intervals. There were 2 poles, right, on the k-naught plane at omega p and minus omega p, right? And to get the Feynman integral, we did this integration. Feynman correlate, we got this integration. Whereas the first order perturbation to the propagator, all it does is that it just moves these guys. It shifts the poles to the first order. It just renormalizes your mass. You could view the effect of it as mass being dependent on lambda. So m is 0 plus a correction that is this guy. Minus I lambda delta f of 0 over 2. Yeah.
That is the actual physical mass.
Yeah.
When you go and measure the mass.
Well, okay, we've not talked renormalization group yet. So yeah, this is infinite. The issue you're pointing out is that this guy, the correction is infinite. That's what you're saying. All right. So it looks like the mass has been renormalized, and this renormalization of mass has a name, self-energy. Right? Self-energy is also referred to this diagram. This renormalization of mass is the first order correction to the propagator in lambda phi 4. And yeah, good. If you had lambda phi cube, could you get a first order correction to the mass? If you think integrals, that might be a headache, but diagrammatically, it's pretty obvious you cannot, right? Because your vertices will have only 3 lines. First order correction means a vertex and 2 lines. How are you going to connect them? You cannot. Right? So this is one of the millions of advantages of diagrams. But as I said, the correction to the propagator, the mass renormalization is infinite. We need to cut it off, and we have to make sense of this later in renormalization theory. Good. Actually, let me see how many. Oh, okay. Are there any questions? Let me pause here. All right. So what do we calculate? We string your Dyson equations to calculate the generating functional of the lambda phi 4 theory to the first order perturbation theory lambda. Using that, we calculate the first order correction to propagator, which was due to this diagram, and this diagram contributed to renormalization of mass by an infinite amount that we're going to push under the rug. Right? In the remaining 10 minutes, because we calculate the partition function at first order, generating functional at first order, I'm going to calculate the correction to a 4-point function. Right? So we're going to get a connected 4-point function. Can you guess what diagram it is? So it is a first order correction, and it has to be connected. First order means what? It's minus I lambda. By the laws of Feynman diagrams, only minus I lambda appears at the vertex. I should have 4 external legs, right? And I have to attach these guys. And it has to remain connected. That's the only thing that I can get. So this. I could have tried to do things like this, but this is not connected. These do not contribute. Well, they're cancelled by the renormalization, but when we divided that 2 terms, there were these 2 terms. Term, oh God, where was it? Oh, I passed it. This term 2 takes care of these guys. But you don't know that yet. All right, good. So this is what the diagram is going to be. And you know what the answer is. But fine. What is this? Minus I lambda. But let's just do the calculation. So the 2-point function, 4-point function for the free theory was this. So the connected piece of it is going to be this, and that's what we're going to calculate. Very good. So because we want to calculate the connected piece, I'm telling you in advance, start with minus I ln of z, because this is the generating functional for the connected piece. But if you don't believe me, take derivatives, 4 derivatives of this guy with respect to delta j, and you'll find that it's this. What is this? This is the 4-point function minus 3 pairs of 2-point functions. Precisely the ones that we got in the free theory. So this is the connected piece. So this is the 4-point function minus 2 point, 2 point, the other two other permutations. Do you guys know a name for generating function? You know the generating function. What do people call log of the generating function? The log of the generating function generates the connector correlator. What is that called in math or physics? Or probability theory? What's that? Can you repeat? Log of zj generates connected correlators. Zj is called partition function or generating function. What is the name of log of zj? So physicists, log of z beta, they call it free energy. Log of zj, we give them different names. Log of zj, we call it effective action. What is that name in say probability theory or math? Like you just have a generating function and you take the log of it and it just always generates the connected correlators. That's a name. Cumulent generating function. That's the name of it. So if you've heard those words, that's what it means. All right, so that was boring. G4 at order lambda squared. Actually, am I going to be able to? Oh, yeah, I can do this. So what does G4 at order lambda 2 looks like? There are 3 diagrams that you could draw. So instead of taking their integral, your expression, expanding them, you just draw all possible diagrams by the laws of Feynman diagrams, right? So you have 4, 1, 2, 3, 4 in point insertions. You have to connect them. Now you need 2 vertices because it has to be second order in lambda. Each vertex comes with an order of lambda. And these are all the diagrams you could draw that. All right. So these are related by symmetry to the first one. So let's just look at the first one. What is this? In real space, laws of Feynman diagram. So minus I lambda for each vertex. So there are 2 of them. 1/2 is a symmetry factor. Interchanging the lines, think about why that is a symmetry factor. There is a propagator here. That's this propagator. There's a propagator here. So there are 2 of them. You have to integrate over x and y. Here's the integral over x and y. X1 and x is this. X2 and x is this. X3 and y is this. X4 and y is this. Good? So that's what this diagram is. Let's do the integral. Let's Fourier transform it. If you Fourier transform this, well, you're going to Fourier transform the external guys, and then the internal one as well. Similarly, you could do that. So you're going to have K1, K2. I should not say external. Yeah, K1, K2, K3, and K4. First thing that you learn is that you're going to get a Dirac delta function of K1 plus K2 minus K3 minus K4. That's not surprising. What is that? Energy momentum conservation. Right? You get a propagator in momentum space for each of these guys. This is always there in any Feynman diagram. So we usually just drop this piece and talk about what is called the amputated diagram. Amputated diagram means that the legs outside, we just don't write them down. Right? We're talking about the amputated ones. That's what I did when I wrote this as this 1 plus this thing, whatever it was, right? This was the amputated diagram. So we often just focus on the amputated diagram because that's all that is important. The rest of it is kinematics, right? The rest of it is completely fixed by kinematics. All right, so we want to evaluate this integral. This is a loop integral. There is a propagator with momentum p. There is another propagator with momentum k1 plus k2 minus p, of course, because the conservation of momentum. And these are time order, therefore I epsilons everywhere. Okay, so we will come back and do this calculation. We'll have to renormalize it. Yeah, go ahead.
Yeah, that's what I was saying. Like this can diverge.
Yeah, it does diverge. We'll talk about renormalization of it, all of that. So this is divergent, but what this is a two loop, second order lambda squared correction to the 4-point function, right? Now, in summary, here are the Feynman rules in momentum space. Every time you have a vertex with 4 momenta coming in, conservation momentum, the sum of all momenta should add up to 0. So there's a Dirac delta function there. And because there's a vertex, it's minus I lambda. Here's a propagator in momentum space. You know what that is. It's I over p squared, k squared, k mu minus m squared plus I epsilon. For internal legs, we always integrate over the all momenta. That's obvious, right? Because that's an extra variable we must integrate. And then you have to divide by the symmetry factor of the diagram. These are Feynman rules in momentum space. All right, so what did we do? We considered some general interaction for a scalar field. We wrote down exact equations that the generating function of the interacting theory has to obey, so-called Schrödinger-Dyson equation. By taking repetitively derivative with respect to j from this equation and setting j equals 0, we get an infinite set of formal but exact equations that correlation functions of quantum field theory fully non-perturbatively will have to satisfy. Example was this for lambda phi 4. Next, we expanded these correlators in lambda. And then we found Feynman rules as a way of organizing this like a craziness of integrals, right? And these were the Feynman rules that you want to remember. You in momentum space, every time there's a vertex, there's a minus I lambda coming from the lambda phi 4 interaction. And then there's conservation of momenta. There's a propagator. The internal loops legs we integrate over, and then there's a symmetry factor to avoid overcounting. Are there any questions? Yeah.
So the entire road led by Schrödinger-Dyson equation was that I wanted to derive how to write the correlation functions in terms of functional derivatives of the generating function.
Yeah, that's the job of the generating function. It's supposed to give you all the correlators. But what we did in Schrödinger-Dyson was by, the way we used it was that we basically got rid of Zj. We related the first derivatives and all the different derivatives to each other. And we got a sequence of them, right? Because the idea was that Zj had to satisfy some differential equation. By taking derivatives, we saw that this implied an infinite set of equations that correlate have to satisfy. As a matter of fact, those equations are equivalent to this.
So that is important for the dynamics of the correlators.
It's a whole theory. The theory. This is at this level, I'm not even distinguishing dynamics from kinematics. The quantum field theory is correlators. That's what it is. Right? And then the beauty of it is that if you must calculate like somebody comes to you and says, I'm doing a calculation of endpoint function something to order lambda 4. All you need to know is one function. All the information content of quantum field theory, lambda phi 4, or your favorite theory, up to a certain order, is captured by only a function, z of j. This is a function. Functional. But that's all it is, right? That's all that it means. So how do people do calculations? Let's say Steinwell particle physics or some theory. Some guy goes and spends 10 years of their life, not a person, like the whole group, calculates this, gives it to people, and then people take this and run with it. A lot of people don't do loop diagram calculation, but people have calculated this. So once and forever, they give you these expressions that this is all the information content of this quantum field theory, repackage it into a function. I'll just take care of this. What does this mean? It means that they're basically, so if you had the classical field theory, all the information content was in an action, right? I gave you the action, just take derivatives, you know everything about it. Don't forget about taking derivatives. You know everything about it. Log of this is called effective action because it's a quantum corrected action, right? It's just still functional that you take derivatives of it and it gives you all, it generates all the correlates. So the quantum field theory is replaced by that function, functional. It's effective action, right? That's the magic of mathematical. It replaces quantum field theory with just a calculation of a functional. That's it. That effective action is not an action of a particular particle propagating in space, but it captures all the quantum corrections. All right. Any other questions?
What is the motivation of coming up with this function? Like, how do you design it? Like, what is the motivation?
What is motivation? Well, solving quantum field theory.
I mean, how do you design it? Like,
how do you design? Well, I just calculated this in one loop for lambda phi 4. And once I give you that expression, now you can do your favorite correlation function calculations starting from that. You don't need to know anything about quantum field theory. You just need to take derivatives. You need to know derivatives. Differentiation of functional. That's all you need to know. Right? This is called good. This is how, in practice, we deal with quantum field theory. Now, hopefully, the word effective action is clear. Why it's called effective action. I'm simplifying a little bit, okay? We're going to come back to QFT2 and do this properly. But this is the gist of it. All right. Thank you.
You did course with remote.
Say it again.
You have two remote courses.